Okay, today we wrapped up the discussion of the Bernoulli equation using a specific example of flow around a cylinder where we have a velocity approaching the cylinder, a velocity v0, and an ambient pressure p0. The streamline that goes right to this leading edge of the cylinder again results in a stagnation point, which is mirrored on the back because of the symmetry of this particular flow. And specifically here, I'm assuming irrotational flow. Irrotational flow allows us to both have this particular solution for the velocity field, but also apply the Bernoulli equation anywhere within the fluid. The streamlines on either side of the stagnation streamline split, move back together again, and the key thing is that along the lateral edges, the velocity increases as the fluid goes around the cylinder. What that means in terms of pressure is that we go from an ambient pressure P0, velocity V0, and by using Bernoulli equation we can see that the pressure has to increase on the leading and trailing edges of the cylinder because the velocity goes down. So as velocity goes down, pressure goes up. Alternatively, along the lateral edges where the velocity increases, the pressure goes down. So I'm just putting minus signs here to denote low pressure. Symmetry of the problem means that there is no net force, which we'll explore more in the context of wakes and drag forces later in the term. Really, this was just a chance to illustrate the fact that as velocity decreases, pressure increases, and vice versa, which you can see from the Bernoulli equation. Then in preparation for Friday, we started talking about the Reynolds transport theorem, and specifically defined three new quantities: the control volume and the control surface. The control volume and the control surface, which I denote as the control volume as CV, the control surface as CS, are both made up of a volume sitting in space, which I'll denote in blue here, through which fluid moves. So the control volume is inside this volume. The control surface is the bounding limit of the control volume. Now the fluid moves through this surface in a way that we'll need to account for when we define the Reynolds transport theorem. The other new term we defined is the system. Now the system is kind of an awkward term, but what it represents is a collection of fluid parcels that we can track in a Lagrangian sense. And so the system here might be this volume of red particles that we can then track as it moves into the control volume and then back out again, allowing us to think about the conservation laws in the fixed reference frame. So what we're going to do on Friday is we're going to develop a statement that describes how the characteristics of the control volume evolve in view of what's happening to this system, which accounts for the fluxes through the control surface. Okay, so those are the building blocks that we're going to need for the derivation of the Reynolds transport theorem, which will start on Friday.